Hey guys, so today we're just going to go over a little more into piecewise functions. So they're just pieces of two different functions graphed together. So when you're looking for the domain of a piecewise function, we're going to address all the x values that the function can be. But again, we do that by seeing what x can't be. So instead of listing all the numbers that x can be, we'll list all the numbers that x can't be to kind of use process of elimination. Now, remember that restrictions, they're not a lot of them. You can't take the square root of a negative, so it always has to be greater than or equal to 0. When you're dealing with a rational function or pretty much a fraction, the denominator can't equal to 0. And these are the restrictions. We don't have that problem in the first function, which is the cube root of x plus 6, but the cube root is just taking the cube root of x. So when you take the cube root of any value, you're basically just taking that number to the 1/3 power. So if you plug a negative number in and you type it into the calculator, -5 to the, and in parentheses, 1 divided by 3, this is how you would plug it into the calculator, it would come out as an answer. You can take a negative, cube root of a negative. If I put 0 and take the cube root of 0 or put it to a 1/3 power, it'll also give me an answer. And the same thing with a positive number. The cube root of 8 or 8 to the 1/3 power would be 2 because 2 times 2 times 2, I multiply it by itself 3 times, would give me 8. So I have no restrictions for the first one. For the second one, again, I'm not dealing with a square root. There's no fraction. Pretty much if I plug a negative value into x, I'll get an answer. If I plug 0 into x, I'll get an answer. And if I plug a positive value into x, I'll also get an answer. So since all x values work for both of these, my domain for this particular answer would just be all real numbers, -infinity to infinity, or in set notation, x such that x is an element of all real numbers. So just diving a little more into piecewise functions, let's say I'm looking for the x-intercept of the piecewise function. So remember that x-intercepts are points on the x-axis. They're points on the x-axis. Algebraically, y is 0 because any point on an x-axis, let's say 1, that y value is 0. So x-intercepts are points on the x-axis. They're also known as zeros. They're what you solve for when you solve for x. So these are all interchangeable. So what I'm going to do here for this particular piecewise function, which missing the little bracket, is that I am going to find its x-intercept by just setting g of x or y equal to 0 for each individual one. So for x to the 3rd power minus 25x, I'm going to set it equal to 0 and solve from here. You got a GCF going on. You have x as the GCF. You're left with x squared minus 25 because if you divide x to the 3rd power by x to the 1st power, you're left with x squared. And if you divide -25x by x, you'll be left with -25. And you can always distribute to check if your factoring is correct. Now, what you could technically solve from here, but I'm going to take your factoring a little further. Remember that in slide 2 and 3, we do go over algebra factoring, and this is known as a difference of squares. You can factor it by rewriting it as x squared plus 0x because the x is missing minus 25, or you can recognize that it is a difference because it's subtraction of two perfect squares. And when you factor a difference of squares, there is a shortcut to it. One parentheses always says plus, one says minus, and you take the square root of each perfect square. The square root of x squared is x. And the square root of 25 is 5. No need to worry about the negative or minus sign in front of the 25 because remember, this is called a difference of perfect squares. So that's already taken into account into the shortcut. So difference is already there, the minus sign. So If you FOIL or distribute it, it'll bring you right back up to x squared minus 25, which shows that your factoring is correct. Now, from here, it's factored, the other side is 0, which means we can just set each of our factors equal to 0. So if I set x plus 5 equal to 0, I'll subtract 5 on both sides, and I'll get x equals negative 5. If I write x minus 5 equals to 0, I'll add 5 to both sides, and I'll get x equals to 5. Now these are my 3 values of x, or my x-intercepts, but remember that there is a condition. This is a piecewise function. You can only use it for x values that are less than 5. So this is fine, this is fine, this is not. Moving on to the next part of the function is negative log base 5 of x minus 1 plus 2. Remember, we're setting y or g of x equal to 0 to find our x-intercept, because x-intercepts just mean you're going to make y 0. First thing I'm going to do is I'm going to subtract 2 on both sides. Negative log base 5 of x minus 1 equals negative 2. Now you do have different options here. Technically you could condense it by changing this coefficient to an exponent, but that would make things more difficult by giving your binomial a negative power. So instead it's being multiplied to the log. I'm going to divide both sides by what it's being multiplied by, which is negative 1. So this would give me log base 5 of x minus 1 equals 2. When you have a log on just one side of the equal sign, you can rewrite this in exponential form. Remember, base to the other side. 5 to the second power equals x minus 1. So base to the other side equals to whatever you're taking the log of, which is x minus 1. So this pretty much gives me 25 equals x minus 1, and I'm out of room here, but you'll add 1 to the other side, and that'll give you x equals to 26. Now, remember the condition. It says I can only use this if x is greater than or equal to 5, which it is. So these 3 values that work within the condition are my x-intercepts of this piecewise function. All right, guys, I hope this helps.